this example, we're looking for the fourth derivative of a power function, also of degree 4. And we're going to try to recognize a pattern here, which obviously I don't think we'll see initially until we go through all 4 derivatives, and then hopefully you see a pattern along with me here, which you can exploit in other practice problems and other examples requiring higher order derivatives of a power function. But keep in mind, to utilize this pattern that we've yet to see here, the number of derivatives you're taking has to match the power degree of the power function. So let's just get away from Leibniz notation for the time being, and we'll just write y equals x to the power 4. And we'll go ahead and get our 4 derivatives. Remember, differentiating a power function is pretty straightforward. Our first derivative using the power rule will be 4x cubed. The second derivative will be 4 times 3, which I guess we can condense down to 12, 12x squared. Our third derivative is 12 times 2, or 24x. And then here we are at our fourth derivative, and I think I'll opt for the brackets around that 4 instead of 4 prime symbols, which looks like tally sticks at this point. Anyway, the fourth derivative is going to be a constant, 24. So trying to recognize a pattern here. Now clearly we end up with a constant if the number of derivatives we take matches the degree of our power function. So the question is, how do we know what that constant is so we don't have to go through all the derivatives? Which is not a big deal if there's 4 derivatives, but if there's 10 or 11 or 12, depending on the degree of our power function, we'd obviously want to find a shortcut around all of that. And that's pretty easy to do if we just kind of remind ourselves where some of these coefficients came from. So our first derivative, nothing has to really change there. That was our power 4 came down. So that was 4x cubed. Now just to remind you, that second derivative, where did the 12 come from? Well, of course, we sidestepped the 4 and we multiplied by the derivative of x cubed, which is 3x squared. And we'll keep doing our derivatives this way, and I think you should see the pattern along with me here. If I sidestep the 4 now, try to get a dot there, sidestep the 4 and the 3, and then we're able to differentiate x squared, and that brings us to our fourth derivative. And I'm not condensing anything, of course, because we need to see our pattern here. We're going to sidestep the 4, the 3, and then the 2, and then I'm going to multiply by the derivative of x, which is 1. And hopefully you recognize that notation, the descending product, 4, 3, 2, 1. That is our factorial notation. So this 24 was actually just the degree of our polynomial, factorial, 4 factorial. Now please keep in mind, we have to take all 4 derivatives in order to be able to use this shortcut. And before we finish here, let's just generalize this to any degree. So if you're taking, we'll use Leibniz notation again. So if we're taking the nth derivative, remember these aren't exponents here, they look like it, but it's saying you're taking the derivative n times of a power function to the power of n. We know we're going to end up with a constant because of all those repeated derivatives. Our final derivative is going to be the constant n factorial. So that's a nice little shortcut that you can't use too often, but you can use it in at least a couple of practice problems. And also keep in mind, even though we're exclusively working with power functions here, that the same concept applies to all polynomial functions of degree n, because eventually at some point all of your other terms are going to disappear by taking higher order derivatives. But anyway, there it is. There's our shortcut. And in future examples and practice problems, like I said, feel free just to say, hey, I know this final derivative here, whether it's the 4th, 5th, 6th, or the 20th derivative, is simply going to be 20 factorial or n factorial, and save yourself a lot of time and effort. Why not? Let's use Wolfram Alpha and just take a quick look at how we can apply our n factorial trick to polynomials in general, not just power functions. So how about the second derivative of a quadratic, which of course is a degree 2 polynomial. And if we take the first and second derivative, we're going to lose a lot of stuff. We're going to end up with a constant. Again, you can do that derivative probably quickly in your head. We'll end up with 2x minus 3, and then the second derivative wipes out the constant 3, and we're going to be left with 2 times 1, or 2. And let's jump to a fourth derivative. And we'll just stick a couple of terms in front here. Of course, a power of 4, and how about a 5x cubed? And we'll stick a plus in there. So that's definitely a polynomial of degree 4, and if I take its fourth derivative, we're going to be left with 4, 3, 2, 1. Multiplied together, which is 24. And one last one, I don't think I'm going to bother typing in too many terms here. We'll just put in a leading x to the power of 10, and we'll keep all that stuff. Guess what? This number is going to be a little bit bigger, but that is 10 factorial. If you don't believe me, what is that? 3.6 million. There's 10 factorial. I guess it already was on the screen there, but there it is, 3.628 million approximately. So that shortcut obviously works great for power functions, but it'll also work for polynomial functions in general, provided that number of derivatives matches the degree of your polynomial function.